Welcome everybody to the combined Denver Java Users Group and Boulder Java Users Group. I'm Greg Ostrovich, and I'm going to go through some announcements, a little bit of housekeeping, and then we'll have our featured speaker. Thanks for joining in. So just a reminder, we're always looking for speakers at the JUGs, at both the Boulder and Denver JUG. Email myself, Matt Rabel, Swoina, if you have a talk that you want to present. Let me go through some housekeeping announcements. Because we're meeting online, if you need the restroom, hopefully you can find it in your house or wherever you're watching the streaming event. Tech Systems is our food sponsor, and we appreciate their support. Tonight's dinner, as is the last few months, is sponsored by whatever's in your pantry and your fridge. But we want to give a shout out to Andrew Rawson, Rawson at techsystems.com, or Courtney at techsystems.com, who is our support for that when we meet in person. We are also sponsored by JFrog. They have a monthly July sweepstakes, but tonight everyone has a chance to be a winner. All those that enter the raffle to win a Nintendo Switch at the end of July will also win an Iron Frog t-shirt. You can scan the QR code or use the bit.ly link in the chat box to enter. And I know Mike Zueda, who is awesome and amazing, will put that link in the chat box. Another sponsor, Apex Systems, but they're our beer sponsor, and that's Braden Collop. And if you have staffing needs, please be sure and reach out to them. Tonight's beer is also sponsored by What's in Your Fridge. And I brought something from our beer fridge for tonight's talk. Develop Intelligence is another sponsor. They offer a plural site giveaway when we do door prizes. Ace Van Seal is our contact, and they're awesome and amazing, and they're always looking to hire technical instructors who specialize in several technologies for contract opportunities. Those include Java, Golang, JavaScript, React, DevOps stuff like Kubernetes and Docker, and many others. Reach out to Jarrett, J-E-R-E-T, at developintelligence.com. Amazon is another sponsor, and that's Chris Almond or Sam Ayer. Tons of opportunities and tons of different stacks. Akka is another sponsor, and they're actually who's recording the meeting, the online meeting tonight. NextGen is another sponsor, and their staffing agency, Beth and Sandy Holskin, Beth Crowley. Currently, they don't have any Java developers, but if you're interested, please connect with beth.crowley at nextgeninc.com. And they have a gift card for us tonight. I know Mike will try to handle that drawing. Another sponsor is Agile Learner. That's Venkat's Romanian's company. And they're offering a subscription to agilelearner.com. And if you catch it in the chat, in the broadcast, Mike Zuedo is telling us to put your name in the chat for a chance at the drawing. So, and another sponsor is JetBrains. And we always give away an IntelliJ IDE, although now it's more broad and actually handles a bunch of languages. So again, we're working out the kinks, but Mike will handle those door prizes, and put your name in the chat for that. I want to give a special shout out to Matt Rabel, who's not here tonight, but handles the broadcast and getting us speakers and locations. To Mike Zuedo, who always does an awesome job at the door prizes and some of the other operational stuff. And to Zeddy Chinfang, who does operational stuff, including our social media announcements and getting the word out about the JUG and handling some of the other stuff behind the scenes. I also want to thank Brian Demers. He's a coworker of Matt's who's actually helping us out tonight, and he's doing the broadcast for the stream. And so with that, I'm going to have Brian bring up Chris Swoina from the Boulder JUG, so that he can thank their sponsors as well.
Good evening, everyone. Thanks for attending. This is a great way for us to virtually get out of the house and be with people. It's also a really good way to keep up on technology and to find out what works and what doesn't work. And whenever you get the chance, you should really encourage your coworkers and friends and associates to also attend these meetings. For Boulder, we want to also, of course, thank Tech Systems. They've been big supporters, and Anastasia Alexenko, she's a really terrific person. She's out of the Westminster office. If you have any questions about your career or what's going on in the industry, she's really been very helpful to a large number of our people. We also want to thank Rule 4 Cybersecurity and Emerging Technologies. They've been a big supporter of ours. They're the 2019 Colorado Technology Association Award winners. No Fluff, Just Stuff and UberConf with Jay Zimmerman. They provide world-class conferences and training. Agile Developer, Venkat Subramanian. He does, of course, tons and tons of training, consulting, and he also has his online learning resource, Agile Developer. I have a number of coupons for that. If anybody would be interested in those subscriptions, just contact me through the Boulder Java Users Group meetup, and I'll get that to you on a first come, first serve basis. Also want to thank JetBrains. JetBrains is a cutting edge software vendor specializing in the creation of intelligent development tools, including IntelliJ, which is the leading Java IDE. I do have a few licenses for that. And again, if you're interested in that, contact me through the Boulder Java Users Group, first come, first serve. And finally, O'Reilly Books. They've been a wonderful sponsor for us as well. Thanks, Greg.
All right. And something that Chris mentioned that I forgot and I saw in the slides, No Fluff. They're a huge sponsor. Jay Zimmerman does a great job with No Fluff and with UberConf, and he is doing some offerings that are online technical conferences just because of what's going on now with COVID-19. So check that out. They're always great. They're always technically really good. It's the people that are committers and authors on the topics, and they've actually used the technology, which is awesome. So last thing before I start by introducing our speaker and talking about his topic tonight is if you have any questions, go ahead and put them in that YouTube comment section, in the YouTube chat section, and Brian will ping our host as those come up and ask him about those. So without further ado, let's bring up what we're going to do for tonight. So it's going to be Hugh McKee on Akka Cluster and Akka Typed Deep Dive and a bit of eye candy. And what this talk is about is you may have heard about the actor model. You may have played with the actor model, but for whatever reason, the opportunity was not there to move forward with it. Well, here's your chance to take a look at the actor model with a set of 4 Java projects that run Akka clusters. In this talk, we will install, run, and examine in detail a set of example projects. We will explore the code and translate it into what is happening in running clusters. The projects progressively grow from basic simple cluster with a few simple actors to actors that message each other across the network to cluster singleton actors and finally to cluster sharding. We will also take a look at one of the newest Akka features, Akka Typed. As a bonus, each project includes a bit of UI eye candy in the form of a web dashboard that will help you gain some intuition about the mechanics of Akka and what is happening inside the running clusters. A key takeaway of this talk is that you can download, build, run, and play with each of the projects covered in the talk on your own. Each project also includes a web dashboard that visualizes cluster changes as they happen. And before I tell you a little bit about Hugh, he's given us some talks on this before, and it's really interesting, and I really think you're going to like it. So Hugh McKee is a developer advocate at Lightbend. He's had a long career building applications that evolve slowly, that inefficiently utilize their infrastructure and were brittle and prone to failure. That all changed when he started building reactive, asynchronous, actor-based systems. This radically new way of building applications rocked his world. As an added benefit, building application systems became way more fun than it had ever been. Now he is focused on helping others to discover the significant advantages and joys of building responsive, resilient, elastic, message-driven applications. You can find Hugh on Twitter at MCKEEH3. So without further ado, Hugh McKee.
Thanks, Greg. And thank you, everyone, for being here and inviting me to speak. I'm in this, as you mentioned, Greg mentioned about the talk, it's really going to be looking at these projects. And if you like, they're simple to download and use. So if I've done this talk before, and in some cases, people have grabbed the project and followed along. So it is something that's possible. So if you have Git and Maven and Java available on your favorite development system, I'm going to kind of go through the steps myself to set up these projects and run them. But these sample projects that I'll be showing you, except for the last two, are really intended to be fairly lightweight, something that you could download onto your development system, your laptop, whatever, and play with. So let me start out. I'm going to share my screen. Share the whole thing. All right. So hopefully you're seeing my screen. A fair amount of what I'm going to be covering is about Akka clusters. And as we go through it, I'll be explaining what Akka clusters are, what actors are running an Akka cluster. We'll be looking at some code that does these things, actors that talk to each other and so on, via asynchronous messaging, which is a feature of actors in an actor system, which is what Akka is. But a lot of the focus here is on Akka clusters themselves. And I'll come back to this diagram a couple of times during the talk. This diagram is found in the Akka documentation, and it shows kind of the life cycle of nodes running in a cluster. Because when I talk about an Akka cluster, we're talking about individual Java virtual machines that are started up, and they form themselves into a cluster by talking to each other over some kind of network connection. Typically, each JVM is running, say, in a different container, or maybe on a different virtual machine, whatever. Akka doesn't really care where it's running. All it needs is an ability to talk over the network and the ability to talk to other nodes that belong to the same cluster, and they form a cluster. So this is easy for us as developers to use, but it's actually quite involved at the Akka level to maintain this. So I've got a set of projects that I want to I'll be going through here. There's actually 5, and the first 3 are the ones that are fairly lightweight, that you can download and play with pretty quickly. They don't take up a lot of resources, but they do run a cluster on your machine. The last 2 are a couple of microservices that make up a kind of an interesting microservice system. It's a work in progress for me right now, but it's really incorporating a lot of the features of these example projects, the first 3 example projects, and some more features to build a real system. So I want to, hopefully, if I have enough time, I wanted to show you a little bit about what these microservices do based on using Akka and Akka clusters and actors messaging with each other and so on. So the first thing I'm going to do is I'm going to grab this first project and just clone it, and then cd into its directory, and then just do a Maven clean package to build it. So if you go to GitHub, and my user is McKee_H3, just like my Twitter handle, and those projects are all under my own GitHub. So now that the project's built, one of the things that comes with the project is a set of scripts for kind of for convenience for this demo that's running in this project. And these are scripts that you can use to run a cluster and play with it. So there's a bunch of different commands that are kind of broken down into 3 different groups. There's a group of commands for starting and stopping and doing some things at the cluster level. There's another group of commands that are focused at doing things at the node level. And a node is an individual member of a cluster, an individual JVM running somewhere on the network. And then finally, in another project, we'll be using some of these net commands to simulate one of the dreaded things that clusters fear the most, I think, is network partitions. And I'm going to take you through quickly what that is in kind of a visual way. So in this project, you can just do you can start up a cluster just by doing /akka cluster start. And what that's going to do is it's going to, by default, and you can control this, it'll start a cluster of up to 9 nodes. So right now what's happening on my laptop, I've just got a MacBook on, so what's happening is it's starting up these 9 nodes, and they're up. Yeah, okay, so it's up, but there's a way to get some JSON that tells us, tells about what's happening in a cluster, but that's boring. The more fun, and this is where the eye candy comes in, is that included in this project is a dashboard. So in the I didn't want it to go there. Let me go back. Sorry about that. Let me do it again. I wanted it to go to this browser. Try that again. There we go. Okay, so this is the dashboard, and it's just a JavaScript thing I wrote. It's using this very awesome JavaScript library called P5.js, which is what I'm using to kind of position things on the screen here. But the main thing is that this is a visualization of this cluster running. So on the right side, you can see there's kind of this 3x3 grid, and each cell in the grid represents a single node in the cluster. So for example, this first cell is showing node 1, and then this map, it's showing the whole cluster. But the reason for this, its own a map of what the cluster looks like, is that this is what the cluster looks like from the perspective of this node. So this cluster started up with 9 nodes. 9 JVMs have started. They started talking to each other over the network. They communicate with each other, and they form themselves into a cluster. There's a lot of background conversations that goes on at the Akka level that we don't have to worry about as ourselves as developers. But the end result is that it forms itself into a cluster. So each node in the cluster has kind of its own little mind map of what the cluster looks like. So from the perspective of node 1, which is running on port 2551 on localhost, it can see that there's 8 other nodes running in this cluster. And that's repeated. And the reason for this dashboard is that each node has to know what the cluster looks like, and they have to collaborate with each other. On the left in the dashboard, what's shown is the perspective of one of the nodes in the cluster. And in this case, it's the node that's on port 2551, which I'm calling node 1. And it's also known as the leader. And I'll explain what the leader is in a moment. It's not super important. It's not a master. This is the Akka cluster is a masterless cluster. In many cluster implementations, there's a master node, and then there's, say, worker nodes that the master node controls. In Akka, they're more collaborative. There's nobody really in charge, but the leader does have a specific role. But any node in the cluster can become a leader, and there's a well-known way for every node to know where the leader is. So, and I'll explain that in a little bit. But the idea here is that in this dashboard, I'm trying to visualize this running cluster. And the reason is that there's things like if nodes come and go from the cluster. So for example, I can stop a few of the nodes using the script. So that, let me cd into that directory first. I can stop a couple of nodes there. Okay, I'm going to stop nodes 1 and 6. So if I hit the stop on this, you can see in the dashboard, because the dashboard's constantly monitoring the cluster. And you can see nodes 1 and 6 drop out. But you can kind of see the state propagate, this state change propagate through the cluster in the dashboard. So this is a live view of this cluster. So now what we're seeing is that node 1 is gone, node 6 is gone. But this little mind map from the perspective of each of the nodes, the remaining nodes, shows that node 1 and 6 is down. So these other, what I'm trying to visually show here is that these other nodes know which nodes are in the cluster and know that those two nodes left the cluster. So this is an example of nodes leaving the cluster in a graceful way, where they actually are doing a JVM termination, which triggers a sequence of events from each of those JVMs to announce to the cluster that they're leaving the cluster. And it's a very well orchestrated process that we just saw happen over the course of a few seconds. Now, to show something a little bit more interesting, you can kill a node. And this is where the node just disappears, like, it just goes away. So now what we're seeing, I killed node 7, so you see it's gone. But from the perspective of the remaining nodes, the 6 remaining nodes, that it shows that node 7 is in this unreachable state. So what's happening in Akka is that this is the life cycle stuff. For example, it's showing. Let me zoom in here. Yeah, that node 2, 3, and so on, they're in an up state, but node 7 is in an unreachable state. And this is what's back in this life cycle diagram. The nodes, when they start up, they initially go into a joining state, and then they'll go to an up state. And then notice this arc in the diagram, it says this is a leader action. So this is really showing the role of the leader. The leader is responsible. The single node in the cluster that is responsible for announcing that, yep, this node looks like it's up. Everybody in the cluster that's running should agree that this node is up. But the decision is made by the leader. I'll show you a weekly up in a moment. But then when I stop those nodes, the up node went from it was running and it was an up state. It dropped to a leaving state. And then when everything was good, the leader said, all right, this node is exiting, and then the leader removes it from the cluster. And then that propagates, it is communicated to the other nodes in the cluster. And then there's also this down state, which I'll show you a little bit as well. So back on the dashboard, we're seeing the situation where node 7 is down and is unreachable, and it's red, and it's in a bad state. And I highlighted that the leader is kind of in this unhappy state, and that with the kind of just showing the red L, and in the background here up in the top left, that the leader's in an unhappy state. Also note though that the leader used to be on the first node, but when I stopped it, it had moved to the second node. So the location of the leader is very simple. It's the node in the cluster with the lowest IP and port. And in this case, all the nodes are running on the same IP, local host. So it's going to go to the lowest port, which is now 2552. So in any case, the leader will move around, and it's got a very simple algorithm that any node can use to know where the leader is in the cluster. But the leader's in this unhappy state. And what that means is that, say I want to bring back or try to bring back nodes 1 and 6. So I can do Akka node start 1 and 6. And what we should see in the dashboard is those guys will start up, but they're stuck in this weekly up state. And the reason that they're stuck in the weekly up state is that the leader knows that there's at least one member in the cluster that's unreachable. Now, the situation here is that all these nodes, in order for them to know what's going on, they're all chatting with each other. The actual term they use in the documentation is they're all gossiping with each other. So there's this constant communication going on between the different nodes. kind of saying, "Are you there? Are you okay?" And, and they're just chatting with each other. So when I killed node 7 suddenly stopped responding. But from the perspective of these other nodes in the cluster, they don't know, what happened. Is node 7 still running, but it can't talk to us? Did node 7 crash? The only thing that these other nodes know is that they can't talk to it. They have no idea what's going on with node 7. Now, of course, we know that the JVM was killed, but from the perspective of these other nodes, the only thing they can know is that the communication between node 7 and everybody else stopped. So when the cluster is in this kind of a situation, it's in a bad state, because it could be that node 7 is still running, but it can't talk to the rest of the cluster. But it could be also that there's actors that were on that node that were supposed to be doing specific work that we don't know if that work's still being done or not. And the way Akka works is that actors are distributed across the cluster, and in some cases, specific actors are responsible, say, for doing specific work with a specific entity, say in a database, like an order. There's an actor that's handling all the interactions and database operations for a particular order, and that actor, say, happened to be on node 7. Well, we can't start another actor up in one of the other nodes in the rest of the cluster, because we don't know if node 7 is up or down. We're in this bad state. So if we try and add some new actors, new nodes, which could possibly run more actors, the leader isn't going to let that node completely join the cluster. It's going to leave the node in this weakly up state. And that's back in the diagram. That's what's being shown here, is that these nodes are in a weakly up state. Now, there's one way to fix this, is that we down node 7. So there's another script for that. It's just Akka node down, and then the via, it's not Akka node down via to down node 7. So what that means is that send this message to node 2. I could change it to node 3 or whatever, and just ask the cluster to down node 7. So I'm going to enter that command. So what we should see is that node 7, the red goes away, it goes down. And then we also saw that the 2 nodes that were stuck in a weakly up state now are promoted. They're up and running. So this is just a kind of a quick example. So the fun part, I think, and what I was hoping with this project, is that for people that are trying to maybe learn about nodes running in a cluster and see what's happening, and things like that, instead of just looking at log files or JSON coming out from Akka management and stuff like that, something visual like this would be hopefully a better learning tool. So I'm going to move on from this project, and let me stop this cluster. Let me do it in the other one, so you can see it happen. I'm going to stop this cluster and install a new one. So Akka cluster stop, and what we should see, everybody goes down, and everything should shut off here in a moment. All right, so this cluster's down. I'm going to kill this tab. And I'm going to go back here, and I'm going to clone another project. CD into that directory. You could do yourself if you're interested. Even clean package to build it. So this SBR is split brain resolver, and split brain resolver is a feature of Akka cluster that helps to resolve situations where a cluster has gotten into kind of a weird network state. I'm going to start up this cluster, and wait for it to come up. There we go. And bring up the dashboard. That's not good. All right, it's the same view, but this project's a little different in that it's got these commands added for creating a network partition. This cluster also started where the first 5 nodes are running on localhost 1, and the last 4 nodes are running on localhost 2. So the script, I've already done this, but there's a, for iOS, on Linux, you don't need to do this, but on iOS, you need to enable packet filtering. So there's a script that does it. You have to be able to sudo it to make it work. And then there's other scripts for creating localhost 2. And then finally, there's a script for turning on or off a network partition. So what I'm going to do is turn on the partition. What the heck's going on? Oh, that's what's wrong. Okay. I'm going to turn the partition on. So what we should see, right? We should see in a moment. There it goes. So this happens, I only have about 15 seconds before it starts to heal itself. But you can see the first 5 nodes, they can see each other, but they can't see the bottom 4 nodes. But if you look at the bottom 4 can see each other, but they can't see the top 5. So this is a classic split brain. So now what happened was that the split brain resolver, which again is part of Akka, is set up to see this kind of situation and resolve the issue. So what happened? Well, these 9 nodes were cut off from each other. The first 5 could see each other. The last 4 could see each other, but they couldn't talk across the IP. You know, so the partition was at the IP level. The 127.0.0.1 couldn't talk to 127.0.0.2, and 2 back to 1, they couldn't talk to each other. So effectively, the 5 nodes were split off from the 4 nodes, but they were all still running. So this is tricky because now we've got 2 clusters running basically. Well, we used to have 1 cluster, now we have 2. And both of these clusters independently and at the same time have to decide to resolve this issue. So what happens is that on both sides of the split brain resolver runs, and it starts doing its processing, where it is there's a strategy that's called keep majority. There's other split brain resolver strategies, but the most common one is keep majority. And what that means is that the side of the partition that has the majority number of nodes wins. And when there's a even split, there's a deal breaker, tiebreaker. I think it's the one with the lowest IP wins. But basically, it's the side of the partition that has the most nodes of the nodes that used to be running. So in this case, there were 9. So we had 5-4 split, and of course the 5 side won. And so the 5 nodes on the winning side said, all right, we're going to continue to run, and we're going to automatically down the 4 nodes on the losing side. At the same time, the 4 nodes on the losing side had to just realize, oh, we're on the losing side, therefore we need to stop ourselves. this isn't a coordinated effort because all these nodes can't talk to each other across this partition. So it's a tricky thing, but there it is. This is how the split brain resolver works. In the past, the split brain resolver was a commercial feature from Lightbend. Now it's part of the open source. So this, I think, is really critical. You really have to have a split brain resolver. There are very good open source split brain resolvers around, so it wasn't that huge of an issue. But now you get the one from Lightbend as well, is an option to use it, and it is part of the open source. And it just is a critical thing because in the wild, people typically see partitions happening. In my experience, was like once a week. You would see a partition happen, maybe once a month or something. They happen. Sometimes they happen way more than you would think they are. Networks are really flaky, and you learn how flaky networks are when you start doing any kind of network programming, or programming where processes on different systems start talking to each other over the network and expect all the traffic to work, and then you get these little intermittent issues where the communication breaks down maybe for a few minutes, and then all of a sudden it just starts working again, and nobody knows why. You talk to the network team, well, the network's fine, everything looks great, but what you're seeing in your system is these really nagging intermittent issues that just cut off communication for various periods of time. Drives clusters crazy. But it's just a fact of life out in the wild in distributed systems. And Akka definitely is a distributed system, and it's it lives and breathes and lives and dies on the network. So this is a critical part. So the partition part is the fun part. So I'm going to turn the partition off. And then I'm going to start those, let's see, what is it? 6, 7, 8, 9. I'm doing this manually here because I'm not running in any kind of orchestration layer. Oops, I'm in the wrong directory. That's not going to help. I hope I didn't screw things up. Sorry about that. I was in the wrong directory when I tried to start script. I think I did. I think I filled it all. What I was trying to do is manually restart those 4 nodes. Now, if you're running in an environment like Kubernetes is like the perfect environment for Akka, because in this kind of scenario, say you do get a split brain, and I was working with a customer for most of 2018, and they were running in an on-premise Kubernetes environment. We had this really bizarre network issue that was just driving us crazy, and it was driving the split brain resolver crazy because we're getting constant weird anomalies in the network. In any case, we were seeing these network partitions occur. But the nice thing is that when, say, the split brain resolver did kick in and shut down some nodes, Kubernetes sees that and goes, oh, wait, this cluster said it wanted 9 nodes, and all of a sudden now it's dropped down to 5. I'm going to spin up, 4 new pods, as they're called in Kubernetes, to bring up those processes again. So this is nice symbiotic relationship between Akka, which is really kind of concerned about what's happening on the inside of the JVMs, in conjunction with something like Kubernetes, which is worried about things kind of at the outside of the JVM, at the process level. And so the nice thing is that there's no manual restarting because the orchestration layer is doing that. So I want to go to a third project. This is the This is this cluster aware project. So let me clone that. Into the directory. Build it. So this project is very similar to the other two, except it's adding a little bit more to it. And now I'm going to start the cluster. And wait for it to come up. Give it a moment. Here we go. Bring up the dashboard. Okay, so this dashboard's a little bit more interesting. I've filled in some of the open area here. And you can see that there's these little like progress bars moving across. And what this is showing is a kind of a visualization of actors that are talking to each other across the cluster. So if I zoom in, let me zoom in on this guy here. So you can see it's saying total pings, and this is from 2551, so it's showing pings that are, what it's showing is pings messages that are coming in from an actor on 2552 and 2553 on through 2559. If you look at 2552, you can see it's showing messages coming in from 2551. Of course, it's not showing a message coming in from itself, so it skips to, and then 3, 4, 5, 6, 7, 8, 9. So this is where the things really get to be a lot of fun, because now we have actors that are talking to each other across the cluster. And this is what I want to kind of show you at the code level, how this is working. But it's also fun at the the eye candy level, this dashboard where we can see this happening. Because the switching to that directory. The reason for this is that, again, things are very dynamic. So each of these actors needs to know who can they talk to across the cluster. So there's an actor running on every one of these nodes. There's a single actor running on every one of these nodes. And somehow each of these actors know about counterparts, the same actor running on the other nodes in the cluster. But what happens if I stop a couple of nodes? So notice I stop 1 and 6 again, and they're going down. And what we should see is the list adjusted. So pretty quickly, the lists in each node shortened by 2. Like 2552 is no longer trying to talk to 2501, or it's no longer trying to talk to 2556. So things just changed. And that's pretty wild, because if you think about trying to do this on your own, basically would be one way to kind of really think about this. Let me start up 1 and 6 again. So 1 and 6 come up, they're in a joining state. You can see it momentarily, they're joining, and then now they're up, and then the list got updated. So let's take a look at the code that's doing this. So it's in this project, the clusterware project. And let me go back to the project. So there's there's not too much code here, but the main player here, the one that's doing all those progress bars, is in this class called clusterware actor. So it's just a Java class. This is, if you guys anybody has worked on with Akka before, one of the most common enhancement requests the Akka team was getting was to make the messaging between actors more strongly typed. So they it took a lot of work, but they introduced what they call Akka Typed last year. So now there's Akka Classic, which is the kind of the untyped messaging, and then there's Akka Typed, which is the new thing that came out last year. So with Akka Typed, they've really made some great improvements to the API. But to write an Akka Typed actor, it starts. There's two types of actors. There's stateful and stateless actors. This is a stateful actor because this actor has some some characteristics that I want to keep in the actor. So the classes, it just extends a base class, and you're saying the type of messages that this actor will accept. There's one method that needs to be created, and it's this create receive method. And here what you do is you're defining what messages are handled by this actor. So actors are again, the actor model was introduced back in the 70s by a gentleman named Carl Hewitt. It's been used in languages in different ways, but most famously in Erlang. Way back in the day, it's still being used. Erlang is still around, and lots of people love it and still use it. The actor model gained some fame back in the 70s, 80s, and 90s, and so on, for things like phone systems, where the phone systems just had to work. They had to work all the time. It didn't matter when hardware was breaking or being upgraded or changed, or things were being pulled out and pushed in. The phone system had to keep working. They couldn't shut down the whole phone system because they had to do a software release or a hardware fix or whatever. So these systems had to be really, really highly resilient and basically unbreakable. And the actor model was fundamentally a very good way to handle that. So that's where one of the areas where the actor model really gained some fame. Back around, it was just over 10 years ago, actually about 11 years ago, Akka came out with Jonas Bonero, and others, Jonas is one of the co-founders of Lightbend, is one of the original creators of Akka, and it introduced the actor model to Java and Scala. So if you look in Wikipedia, there's a great definition. Like, I think that the first paragraph, if you look at the actor model in Wikipedia, has a really concise definition of what actors do. But fundamentally, an actor, the only way you can communicate with an actor is you send it a message, and it's an asynchronous message. So the analogy I like using is you're sending text messages to each other. You send me a message, that's an asynchronous message you sent to me. Now, did I get it or not? You don't know. Will I respond to it or not? You don't know. But typically when we get in some kind of a texting conversation, a messaging conversation, we're sending each other asynchronous messages back and forth. Well, that's very much like the behavior of actors in an actor system. So here in this method is where we're defining what messages, the types of messages that this specific actor will receive, and how that each of those messages is handled. So here there's 4 different kinds of messages that are handled. Two of the kind of the easy ones, ping and pong. So a ping is an incoming message from another actor to this actor saying, hey, I just want to ping you. And then pong is a reply message back from this actor to the actor that pinged it, just to say, yep, I got your ping. Here's my pong message back. The tick is an interesting one, because what that is a something where this actor has set itself up to periodically receive a message sent from, basically, to keep it simple, from Akka. Akka basically is asked to send this actor a message on some tick interval. And in this case, the tick interval is defined here. It's just a duration of half a second. And what that means is that every half second, this actor is going to receive a tick message. So if we follow this tick message, because this is the heartbeat of how those progress bars are working their way across the dashboard. So we get on to the tick method. There's this method called ping up colleagues. And then here's an example of one actor sending a message to another actor, this tell method. So this actor was started and it was passed what's called an actor reference to another actor, which I called just HTTP server actor, which you can, by the name, I think you can guess what it is. And it's passing along a message that contains ping statistics. So this is how this actor is feeding data to the HTTP server so that when the dashboard is requests information to render on the display, that's where it's getting all this data. So this actor is sending a message to another actor so that that actor can, when it's getting HTTP requests, can render that information on the screen. But the ping up colleagues is where the messaging happens between the different actors, how this actor pings its counterparts. So the trick is that there's this list of, that I haven't explained yet, of services or other actors that is has been fed somehow to this actor, and I'll show you how that's done in a minute. And this list is used by this actor to know who can I send messages to across the cluster. So it takes that list and it just kind of filters through that list, and it says, I don't want to send myself an actor, so it says, it's just filter out myself, right? I won't go in gory detail on the logic here. And then also filter out any actor that's on a member, a node. Nodes are also called members, that is not in an up state. So like that weekly up, they wouldn't be participants in this game. If there was a node that was weekly up, it wouldn't be part of this ping pong game. And then finally, it does a tell. It sends a message. It's filtered out itself. It's filtered out anybody that's down, that's in the list. And this tell is, again, how one actor sends a message to another actor. So this this cluster where actor, it's just the kind of the actor URL of the other actor, and it's doing a tell, and I'm just building a simple kind of POJO, and I'm passing back or sending off a ping message to the other actor. The other actor is this code again, but it's running on another node in the cluster. So this other actor gets that ping message. So on ping, we go down to on ping, and all it's doing is I'm just throwing that out into the log, and I'm just doing the ping message contained the address or the actor URL of this actor, the sender actor. So the ping is just replying to that actor reference is called, just saying Pong. But it's sending back the start time. So what I was doing is in the ping message, it contained the nanosecond time of when that message was created. And when the Pong message comes back, it's relayed that time back, so I can get the elapsed time between the ping and the Pong. And I was just logging out for fun. And then it's updating some statistics, which is the statistics that are being rendered on the dashboard, and that's it. So how does this thing know? How does this actor know what's going on in the cluster? Well, it starts out at the beginning, where there's in the constructor of this class, there's this method that's called it's just something I wrote that it's called Receptionist register and subscribe. So this is a new feature of Akka Typed. There's this concept of a receptionist. And a receptionist is a thing in Akka that actors can do two things. They can register themselves to be added to the list of known actors to the receptionist. So you're kind of checking with the receptionist saying, hey, I'm here, I'm in the cluster, and here's where I'm at. And then the other thing you can do with the receptionist is that you can subscribe. So that's pretty simple to set up. Here, this is the receptionist register subscribe. So here is, I'm just doing, the call to the receptionist is just context, which is the actor context. Get the Akka system, which is kind of a critical feature, your ability to talk to Akka. And then one of the things you can talk to Akka is the receptionist. And all you're doing is sending a message to the receptionist saying, hey, I want to register. You're sending a receptionist register message. You're giving it a service key, which is some arbitrary key, whatever you decide that key is, and then you're giving the actor reference, the actor URL. This actor's URL is being sent in that message. So this actor is registering itself with the receptionist saying, "Hey, I'm here, and this is where you can find me. You can find me at this location, which is this context get self." The other thing it does is it sends another message to the receptionist saying, I want to subscribe to be notified when the list of registered actors changes, when actors are added to the list or when actors are removed from the list. So that's all that's needed for this actor to register itself with the receptionist and subscribe to be notified when things change in the receptionist. Now, the receptionist is something that runs across the cluster. It's the responsibility of the receptionist to propagate this information across the cluster because this actor registers. Let me go back to the dashboard. See the actor on this cluster-aware actor that I wrote. It started up on node 2551. It sent messages to the local receptionist saying, I want to register and I want to subscribe. So the receptionist running on node 2551 needed to communicate to the receptionists across the cluster to say, hey, there's this actor that's on 2551 that has registered, and it's also wants to subscribe to be notified when the list changes. So it's the receptionist responsible for propagating this information across the cluster so that everybody knows what's running, which means, and this is where the kind of the magic happens, because if I stop, say just node, I'll do say 5. I stop 5. So node 5 is stopping. It's doing an orderly shutdown. It's gone. So the receptionist saw that is gone, and it propagated that information to the remaining 8 nodes in the cluster to say, hey, that actor that used to be running on node 5 is no longer there. It's gone. And you could see that the list, shortened. The number of pings and pongs that are happening now don't include that anymore. So that's really all I had to do in my actor to make this work. So it's kind of a trivial example, but if you think about it, the mechanics of this is quite powerful. So I'm going to start up node 5 again, and it comes back online. And when it's up, we see the list get upgraded, and it kind of propagates again across the cluster, and everybody sees, node 5 is back. That cluster-aware actor is back, so let's start pinging and ponging with that guy again as well. Okay, so like I said, this project is very similar to the first 2 I showed you. Each project is a little different from each other. There's a few classes in here. Let's see, this is the cluster aware. There's another actor that is in all the projects, and I call it a cluster listener actor. And all this thing does is it's registered with something else in Akka, and what it's registered to be notified about is when the cluster changes. And what it does is it just logs things out into the log. So before I had the dashboard, the only way to kind of demo this to people and show it in situations like this is I was going into boring old logs, and I was getting tired of that. That's why I wanted to do the visualization with the dashboard. So this cluster listener actor, like I say, if you I won't go into the code, but if you take a look at it, all it's doing is kind of logging out interesting information as the cluster forms itself, or nodes leave or join the cluster or become unreachable. All those events, cluster state events, are being logged in each node's log. The HTTP server actors, and the HTTP server, those guys are, of course, responsible for responding to the dashboard. The runner is just kind of where the main method is at, and this main is actually an actor that kind of bootstraps the cluster. So these are kind of the major players in this class. With Akka, there's a application.conf. This is the type safe config style of doing configuration, and there's a few things in here that configure this cluster. The dashboard JavaScript is included, and I wrote it. I'm not a front end guy, but I know enough JavaScript to be dangerous. But as I mentioned in the beginning of the talk, the P5JS is an awesome way to to write stuff like the dashboard. So it's very cool. And actually, I think it's this one here, the cluster aware dashboard. No, it's just part of it. So anyways, all the source code's there, for the dashboard JavaScript and of course all the Java itself. I don't know if anybody's tried this while I was talking. Excuse me. One of the things I did in the past was.
Sorry, Hugh, we do have a couple questions.
Yeah.
So we have one from Jody, a couple from Jody. So if a ping is the node sending the message, a pong is the response. Does a pong also apply when it's a message received, not in the response?
Say it again.
I'm not sure I understand. I thought I did before I started reading it here. So if a ping is the sending message, and a pong is a response. So I'm guessing that those are the POJOs that you had.
Mm-hmm.
Does the pong also apply when a message is received not in response? I guess I don't. Should have pre-screened that a little better. Sorry.
If I kind of understand the question, I mean, it's like me and you texting again. But it's like you and you texting. You and your clone are texting from two different locations, and so it's the same you. You're built with the same DNA, but there's two of you. Which is it's the same source code running on two different machines. One of us, or one of you, sends a ping message to the other one. The other one, when it gets a ping message, its DNA says, its instinct says, just send back a pong message. So it's a reaction. So it's not the classic request, like the synchronous kind of request response. This is the actor itself was specifically written in the way that when it receives a ping message, its code says, take that ping, build a Pong object, and send it back to the address that came in the ping message. That's it. So it's a reaction. But it's two asynchronous messages.
So Jody, let us know if that doesn't answer your question. We'll ask another one.
Did you have another one?
It did. So I was trying to screen it, make sure I understood before I read it. So here we go. If I have data on a cluster that is intentionally partitioned, that is different from the partition where the connectivity is lost, can you touch on how intentional partitions are handled in clusters? So I'm guessing that means if you have two separate partitions and they need to communicate, maybe, how can you communicate cross network boundaries, maybe? I don't know if that's the question.
I would interpret intentional partition almost be like two different data centers. You know, especially with data where, say, you're geographically dispersed and you have data, replicated data between two different geographic locations. I could be wrong, but there would, with a partition, you really wouldn't. In the context of what I was talking about, a partition is a very bad thing for a cluster. But running in a distributed world where you have, say, almost like two different clusters, one cluster is running in one data center and another cluster is running, in a second data center, and they're also sharing a geographically distributed, replicated database. I'm wondering if that's the question, and if it is, we do have a solution for that. It's multi-data center persistence, but it's what it is that you're building the system so that you built into the logic that that there could be concurrent updates to the same thing. It's like you're building an order or something, and one request goes into data center A to add something to the order, and another request goes into data center B to add something to the order. There has to be some kind of logic and custom logic that is there to reconcile the differences, and that is formally built into this multi-DC Akka persistence is called. In fact, that was another feature that they originally made as a commercial only feature, and I don't think it's out yet, but I think they're very close to making that a part of the open source also.
Great. Jody says, yep. So I assume that was the answer to her question. So great job.
Cool.
All right. So I'm going to drop back off and give it all back to you here.
All right. So, there's, the fun part of this is, I guess, is you can take these projects, you can run them yourselves, you can examine the code, you can play with it, you can do whatever you want with it. I mean, they're there for you to use and go nuts with it. I was hoping that it would be something that would help people to, build an intuition, like what's actually happening in clusters and stuff and so on. And also introducing features like this with this cluster where it's showing maybe a simplistic use case for how actors can talk to each other across a cluster, but this is a very powerful foundation. And there's a lot of things built into Akka that come out of the box that does this, but I found in my experience that there's a lot of things I've done that kind of building on top of this as well, that wasn't that hard for me to do once I kind of wrapped my head around the concepts. And I would look, kind of step back from looking, wow, I couldn't even dream of doing stuff like this before. I had something like Akka. So it really did. It did blow my mind when I started to kind of wrap my head around this and play with it. Which brings me to the final two projects, this thing I'm working on right now. So let me scroll over to that. Here we go. So this is an app that's, the GitHub projects are there. It is a work in progress, so I'm very actively developing it, but it's working. And what it is it's composed of two separate projects because there's two separate microservices that both microservices do event sourcing, which is a different way of, I don't know how many people have done event sourcing, but it's definitely an alternative to the CRUD, something that most of us have been doing for a long time. We know and love CRUD. We have great tools for doing it. CRUD is extremely powerful, and it's extremely mature. But another way of handling data is called event sourcing and command query responsibility segregation. Actually, more appropriately, command query responsibility segregation with event sourcing is one way of doing part of command query responsibility segregation. So what's command query responsibility segregation? There, the idea is that instead of, say, doing create, read, update, delete, you're making transactions where you read some information, you update it, or maybe do some deletes, and then you push it back down to the database. With the command query responsibility segregation, you're splitting the reading from the writing. You're splitting the commands, which are making changes to the data, from the queries of the data. And you're actually physically splitting the data. So on what's called the right side, there's an event journal. And what happens is that commands come into, say, a microservice or something that does event sourcing. Commands are requests to do something, but it's a request. It's to do something that hasn't happened yet. Now, commands go through business logic, they go through validation, whatever, and then if everything's good and the system accepts the command, the system may create one or more events that are the result of that command. So as a simple example, back to the shopping cart, I always go back to that, add item to cart, right? So command is please add this item to a cart. The event is item added, it's a past tense. It's a historical fact. So what gets written into the event journal is just that event. It's some kind of key value structure. It's not very queryable, but it's very fast. And all you're doing is inserts. So there's no updates, there's no deletes, there's very few queries, and it's just inserts. So the idea is it's super fast, and you're just writing. So say in an order, I added that item to the cart and say the quantity is 1, and I changed my mind. Oh, I want the quantity to be 2. Well, that's a second event that gets written into the journal. Change the quantity. The shopping cart itself, which, the entity, that's the state of the order. Each event aggregates to the current state of the order. So I added an item to the cart. Now I changed the item from quantity from 1 to 2. So now the shopping cart says I've got this one item in the cart with a quantity of 2. And that's the result of 2 events that were stored in the journal. So I think you can kind of extrapolate out to building an order. You had the shipping address, billing address, credit, payment information, whatever. And all those things get captured as events. But again, that's not a very queryable data store. So the responsibility for doing queries is segregated to a separate data store, which is called the read side. So the read side is a data store that's optimized for the kinds of queries that you need to perform the query operations that the service or the system needs to do. So the idea is that there is a segregation, and one of the microservices in this system is using both event sourcing, or writing events to a journal, and it's also taking those events, and the concept is that we're using is the events are being projected into a queryable data store. So in this app, the idea is that we got this map, and what am I doing? You can, it's just kind of like Google Maps. You can zoom in and go to some area, and you can see there's these markers in the map. And what these markers are showing is a location of devices. So as I'm zooming in, this is triggering queries to the the query side, the read side, the projection, where I'm getting information about devices that are in this area. Now, what I'm looking at is that in this region, you can see this green box as I'm zooming in closer. There's 15,000 and some devices, whatever they might be. Worldwide, there's almost 19,000 devices. But I'm just kind of zooming in around the Atlanta airport. And it's a simple application, but the idea is that devices either these are like IoT devices. It's just a simple simulation of IoT devices. And IoT devices, in this case, have a simple state. The device is either happy or it's sad. It's working okay or there's a problem. So right now there's some device somewhere, and I'm zooming in, as I zoom in, that what this is kind of representing is that there was one bad device in this location, near gate A17. I travel a lot, and I know this area, the Atlanta airport. I live in Florida, so I pass through Atlanta. I used to pass through Atlanta a lot when I traveled, I just kind of signaled that there's a device here that's unhappy. The part of this, though, is it's a demonstration project where we wanted to be able to push the system hard. And what I mean by this is that I wanted to be able to create a lot of data quickly and also be able to see things quickly. So one of the things you can do with this system is that you can create devices in some geographic area. So if I can basically up in the top right, you can see it says C for create, D for delete, H for happy, S for sad. So I just hit a C, and then when I move my mouse around, it jumps to different geographic regions. But if I click, it's going to create 256 devices in this region. So if I click it, we should see, hopefully, if it's working. I just got this working recently. We should see some devices get created here. Come on, demo gods, be good to me. There we go. It showed up. I was hoping to get a little bit more fine-grained. And then I can zoom in and say, because there's 256, but now I can say, I'm going to make one of these devices sad. I'll make another one sad, and another one sad, and another one sad. And maybe I'll delete one, and then delete another one, delete another one. So you're looking at this and going, wow, this system isn't fast. And it's not. We haven't tuned it yet. So, but what it is showing is that the events that are being written into the journal very, very quickly. But then the events then are being picked up. There's a eventual consistency. There's a latency gap between what you see in the query side versus what you see in the write side, in the journal side. And I haven't tuned the latency yet. But it's not a single transaction. That's another critical feature of event sourcing in CQRS. So in any case, we'll tune it down to make this tighter. But the real fun is that, and the system's not ready for this, is that say if I zoom way out and I say I want to create, no, I went too far. I want to create devices. If I clicked here, what it would send in a request that would trigger the creation of 262,000 devices. So that's 262,000 inserts of events in each microservice. And then the query side, the data is summarized massively at 16 different levels. So there's this huge summarization that occurs that happens on the query side. And I'm using this to kind of motivate the Akka team. And then we're also working with a company right now. It's called Yugabyte. which is kind of a spanner-like database that runs in the cloud, and it scales and so on. So I'm working with them as well to try and build a cloud system that can handle something like this, where say one click and I create trigger the creation of 250,000 devices. If I've actually disabled it in this app, but if you zoomed all the way out, I don't know if you can see the grid in your view, but there's a grid. It's like 20 degrees longitude and latitude, each tile in this grid. And that represents about 1 billion devices. I don't know if we can ever get the system to handle, say, a single request that would trigger the creation of 1 billion devices, which would trigger like 10 or 15 billion database operations within a relatively short period of time. Who knows? But it's fun. So it's a fun app that I've been playing with. I'm also using that P5.js for this map rendering. So all this is written. This whole map part is just JavaScript that I wrote using an open source map that's part of the P5.js library. So these projects, the code is actually not super hard. Of course, there's more code because it's a more realistic application, but the right directory. It's these last two repos. This OTI-sim and an OTI-twin. So OTI-sim is for simulator. What it's doing, it's a microservice. It runs in an Akka cluster. Right now it's running in Kubernetes in Google Kubernetes engine. The nice thing with Akka is I can scale the number of nodes. In testing this week, I've scaled it up to 5. I'll probably scale it way up beyond that. And then, but what this simulator service is doing is it's simulating the outside world. So what happens is that when I do that region select to create a bunch of devices, the request goes into that service. And that kind of cascade, it's a single request. It's a single little HTTP post that says, create devices in this region. And then that microservice takes that and kind of explodes it into however many requests, like the example I showed you was 256 individual devices. So it actually created 256 data entities for each of those devices. And then it sent 256 HTTP messages from the SIM service to the twin service. The twin service is the one that's simulating a kind of a very basic IoT type of Akka microservice. And the reason I called it twin is a guy from Tesla that's big fan of our tech, and he's done a lot of really great talks. Colin Breck, he coined the term, or at least that's where I first heard it. He called it a digital twin. He's working on an application on a team at Tesla where they're doing stuff with the Tesla batteries, and the Tesla batteries they're basically IoT devices, and they're getting telemetry from those things, and they have what they call digital twins, which are Akka actors on the backside that are twins of the physical device in the real world. So I kind of I like that name. I love that name, and so I just used it for this other project. I used OTI for other things, internet, just to I didn't want to use IoT. So you can grab those projects if you've got access to Kubernetes. I initially played with this on Minikube on my one of my development systems. And I also use Yugabyte, which is an easy install. Yugabyte supports Postgres and Cassandra, which is what these microservices use. And I got it working in Minikube. Now, it does eat up a lot of resources, so it might not fit on everybody's machine, but at least you could look at the code if you're interested. So I think that's all that I have. I hope to gave you a little bit of insight into some of the behavior of Akka, maybe inspired you to maybe take a look at some of these projects and play around them, and maybe if you wanted to show other people what you know about Akka in a visual way, take those dashboards and do that. I'm going to be adding more projects with more dashboards as time goes on. So keep an eye on that if you're interested. And I think I'll turn it back to you guys.
All right. Thank you so much. It looks like we have some questions that were there, and thank you, Jody, for asking those. And be sure and reach out to Hugh on his on Twitter, and that's out there. And if you could, the other thing is, if you want to send us any of the decks from the different diagrams you had or anything like that, we can post that as well. I know most of it was the demo. So Hugh, thank you so much for doing this. We appreciate it. And be sure and share this, everybody, with your friends if they want to check out the talk, because it'll be online forever. So thank you, and have a great time. Have a great week, and we'll see you next month.